Okay, testing this out, since no one's in office hours and I can record these meetings, I'm going to work through a problem dealing with static equilibrium. And if someone shows up in the middle of this video, well, that will be pretty amusing. Okay, so this is a problem that I would normally give as a group activity, but since we're not meeting as a group, I'm not doing that this semester, but I had this problem handy. So I'm first going to slide up and show this picture while I read the problem, or you can rewind and freeze frame. But we have this rectangular sine and has a given dimensions that this length A is equal to 1.10 meters, and this width B is equal to 1.3 meters. It's attached to a wall by a single hinge in the top left corner, supported by a cable in the top right corner, as shown in this diagram, and we're told that this angle theta is equal to 25 degrees. The sine has a mass of 195 kilograms, so let's write that down here somewhere. M is equal to 195 kg, and is of uniform density, and the center of gravity is indicated. So this little symbol here is the symbol for our center of gravity. And what that means is for the purposes of torque, we can have our entire weight vector acting at that point. And we will need to know that because this is a torque problem. So coming back over and looking at what we're asked to find, it says A, what is the tension in this cable? And B, what is the magnitude and direction of the force H exerted on the sine from the hinge? And I have these two little footnotes down here. Let's see if I can scroll down so you can see them. The first footnote on finding the tension says this can be determined by only using a torque equation if the pivot point is chosen wisely. So that's a hint we'll use in a minute. And the second says, as shown in the diagram, this hinge force is not a normal force and can point in any direction. It is easiest to first find the x and y components, then find magnitude and direction. Again, this we didn't classify as a separate category, hinge forces. This is just to let us know that we should sort of just treat it as a generic force when we go and start doing calculations. So the tension we're asked to find in the cable is the tension, well, my hand is like right there, is the tension that is acting along this direction. So we have some tension T. So again, we can think of that force that's being exerted at this point there. So we have the tension T, we have the hinge force here that makes some angle, and we don't necessarily know what that angle is yet. That's one of the things we're going to try to find, and we'll call that angle phi. Introduce more Greek letters. And then we have the weight here. So going through and listing the things that we know, and we've already written down everything we know. What we're trying to find is first, we're trying to find the tension. And the tension is just this magnitude, because we already know the direction. It's acting at 25 degrees. So that is going to represent one unknown quantity. That's one variable we're trying to find the value of. And then next, we're asked to find the magnitude and direction of this hinge force. And so notice that I'm writing this as a vector because that's what we're trying to find. We're trying to find the values of this force vector. And in 2 dimensions, that is going to correspond to 2 unknown quantities. So our tension, again, we can get away with just finding the magnitude, but for the hinge, we want to find the magnitude and the direction. So that is going to be 2 unknowns that we have to find. So in total, we have 3 unknown quantities that we're trying to find in this problem. The footnote said it's easiest to find the x and y components, then find magnitude and direction. And those could also serve as our 2 unknown quantities. We could take the x components and the y components, and that could also be 2 unknowns. So whether we write it as a magnitude and a direction, or whether we write it as x and y components, either way, that's 2 unknowns. So I have total 3 unknowns. This means that in order to solve them, we are going to need 3 equations. So And the equations that we're going to use, the equations that we're focusing on this chapter, are the equations for static equilibrium. And those are that the sum of forces acting on an object is equal to 0. Notice I've first written this as a force vector equation. We're summing up all of our force vectors and having that equal to 0. But when we actually go and sit down to do the work, we'll write this as sum of our fx is equal to 0, sum of fy is equal to 0. So that there corresponds to 2 of our equations. And then finally, our third equation is going to come from our torque equation. So we have 3 equations: force in the x, force in the y, and torque. And we have 3 unknowns: our magnitude of tension, 2 components of the hinge force. Now, we could really find these in any order, or could find them all simultaneously, but the problem gave us part A, find the tension first, so let's do that. And the hint also said that this can be determined only using a torque equation if the pivot point is chosen wisely. Now, because this object is in static equilibrium, if we ask the question, about what point is this object not rotating? The answer is it is not rotating about any point on the object. We can choose any point we want to serve as our pivot point, because guess what? If I choose a point, it's not rotating about that point, because it's not rotating about any point. We, in fact, could choose a point not even on our object. So, since we have the freedom to choose our pivot point, we want to do things as we have always done when it comes to math, and that is being as lazy as possible. We want to do the least amount of work algebraically in order to get to our answer. So the first thing we're going to do is we're typically always going to choose a pivot point where one of our forces is applied, what I called a force point, because then that exerts no torque about that point. So already we have the point where the tension's attached, the point where the hinge is attached, or the center of gravity. Any torque about those points is going to be 0. Now, the other thing we want to do is we want to be able to find, with just one torque equation, the value of our tension. So that means our tension and the torque from that tension has to appear in our equation. So if I were to choose this point here, since that exerts no torque, it actually wouldn't appear in our equation, which means I would have to choose some other point. And if I choose this hinge point as the pivot point, spoiler, that's what I'm going to do. Notice the components of our hinge forces, this hx and hy, which at the moment are unknown, are not going to appear in our torque equation. Again, we can write down an equation about any point, but this sort of gets us to the end result fastest if we choose this as our pivot point. So then we only have the torque from gravity, acting at the center of gravity, and we have it from this tension. So now looking at each of these forces, we know that our torque is acting up at this angle. It's going to tend to make things move in a counterclockwise, and so we're going to call that a positive torque. Looking at our weight, that's acting in a direction that's going to tend to move it in a clockwise direction, and so we're going to call that negative. So we're only going to have 2 torques. One's positive, one's negative. They must completely cancel each other out. And so we have to go about starting to compute our torque. So starting at this one for the tension, we have this as our pivot point. The distance r that we would have for that tension is just the distance from our pivot point to where that's attached. We have the magnitude of our tension T, and we have the angle relative to this line. And so the torque from our tension, if we were to start writing down our torque equation, would be positive because it's going counterclockwise. Our value of r is just this distance b. And for the moment, I'm going to keep it in terms of variables and write it as b multiplied by my tension T multiplied by the sine of the angle that that force makes with respect to the radial line. So that's sine of theta. Again, I could plug in numbers for all of these, and eventually I will. But for the moment, I'm going to keep things going algebraically. Now, we then have to compute the torque from the weight. And notice that for this one, things are a little bit more complicated because it's not located on this line. If we were to draw our our radial line, that would be a line that goes this way, and we don't know this distance, right? We'd have to do a little bit of trig, right, with a over 2 and b over 2. We don't know the angle, right? We'd have to figure out that angle and then figure out this angle. But we have these different methods of finding the torque. We don't just need to do r times f times sine theta. Instead, we can either find the perpendicular component of this force, one going in that direction, such that then that force would be perpendicular to our to this distance here, or we can use this method where we find the lever arm, which is I take my force and I find my line of action. It's always an awesome phrase. Line of action. The line of action of that force. And then my r perpendicular, my moment arm, is the distance from my pivot point to that line of action such that it makes it perpendicular. In essence, I can take my force and slide it anywhere on this line of action, and it will always exert the same torque. That's my wife gracefully laughing at my jokes in the background because you're not there to laugh at them for me. And notice that distance is much, much easier to find because it's located halfway. This distance is just b over 2. And so rather than go through all of the rigmarole of finding this length and this angles, which we could, and it would work, we can also just say it's going to be r perpendicular multiplied by the weight. So let's do that. We know it's negative because it's acting in a clockwise direction. So minus our lever arm, which is b over 2, multiplied by our weight, which is just mg. So notice that if we want to, we can plug in that our mg multiplied by 9.8. That gives us 1,911 newtons. But coming back to our torque equation, we said this is going to add up to 0. And here is why I like to do things in terms of variables, because if we just start plugging in numbers, we'll get an answer, but we won't necessarily notice some things that might become important later. So for example, notice here, if I'm trying to solve for my tension, right, I can move that to the other side, it becomes positive. So I have b times t times the sine of theta is equal to b over 2 times mg. And you'll notice already I have b on both sides. So in fact, for this problem, it doesn't matter how wide the sine is. That's not going to affect the value of the tension. And then all I have to do is divide by sine theta to solve for my tension. We get tension is equal to mg divided by 2 sine theta. So it depends upon this angle theta, and it's going to depend upon the weight of the sine. Again, the greater the weight, the greater the tension, which makes sense. If I plug this in the calculator, I have 1911 divided by 2 times the sine of 25. And this gives me a value of 2261 newtons. So that's the value of our tension. We can use that in later calculations. So that's our tension, and we've used our torque equation. So coming back and looking at the things we're trying to find out, we just found out what our tension is, and now we have to go and find out what the hinge forces are. So here, notice our other two equations we haven't used, right? We just used the torque equation, are the force equations, right? Good old Newton's second law for an object in equilibrium. And so for part B, let me give myself some more space here, I have the sum of forces in the x direction are going to be equal to 0, and the sum of forces in the y direction are going to be equal to 0. So those are going to be our two equations. And we've been doing this for a few chapters now. If we go and look at our, get this back into frame here. If we look at our object, we've essentially drawn all of our forces in. We know that if I choose a coordinate system where this is in the x direction and this is in the y direction, our weight is acting purely in the negative y. Both the hinge force and the tension have both x and y components, but we can sort of easily split them up using sine and cosine as we have always done. In fact, continuing to sketch on this figure, we would have some tx going that way. We would have some ty going this way. Same thing over here. I would have some hx and some hy acting on this hinge. So when I first start to go write down my force equations. In the x direction, I have my hx, right? That's positive because it's going to the right. That's an unknown. That's going to be there. And then I have my tx. I have my component of the tension. And so if we want to, we can go and rewrite, sort of redraw this triangle. I know here's tx, here's ty, here's our theta, and then here's our tension that we already know. We already know this angle. Notice that I can say that tx is going to be equal to, again, just in terms of the magnitude, t multiplied by the cosine of theta, because that's the adjacent side, and then my ty is going to be t times the sine of theta. And then we know this is negative, and that is acting positive. But again, we already have the tension. In fact, we've already written the tension in terms of sine theta. And so if I put in, going back to my force equation, there it is, I have hx, this is going to be minus t cosine theta, or hx minus t, and then I'm just going to substitute right in mg divided by 2, no, this was the t, 2 sine theta, right, and then I multiply by cosine theta. And so I have cosine theta over sine theta, which I could turn into a cotangent, but I absolutely hate the cotangent. So I'm going to instead write it as tangent theta. So this will be minus mg over 2 tan theta is equal to 0, and that's gone off camera. So there we go. So hx minus t cosine theta, which was our tx. In essence, we're just saying these two components are going to exactly cancel each other out because the weight's acting vertically. These are the only two forces. So coming down over here, this says we can say that hx is equal to mg divided by 2 times the tangent of theta. Again, we can write it purely in terms of the numbers we were given. If you like plugging in numbers, we can do that. And this gives us 2049 newtons. Similarly, for the y direction, let's move this way. In the y direction, we have the y components of our tension, y component of our hinge force, and then the weight, of course, pulling downward. So we'll have negative mg, because that's acting downward. Both hy and ty are positive, so plus hy plus ty, but ty is equal to t times the sine of theta. And again, all of that is equal to 0. So moving things around a little bit, if I want to solve for hy, give myself even more space. I'm trying to fit this all on one sheet of paper here. I have hy is equal to, that's going to be mg minus t sine theta. Again, here's where it's nice that we kept things in terms of variables, because t I can write as mg over 2 sine theta, put a minus sign in there, minus times the sine of theta, and then sine of theta cancels out. And I'm just left with mg minus mg over 2, and my calculator is too far away, so I'll do that in my head. That just gives me mg over 2. It's supporting half of the weight. Not only that, but if we looked at what we were doing in the first place, our ty, that's what this thing was over here, our ty is also equal to mg over 2. So in fact, our hy, you can't see that. Let's make it so you can see that. Our hy is equal to mg over 2, or just half of the weight, 956 newtons. So those are our two components. But we were asked to find the magnitude and direction, not just the x and y components. But notice that our hx we've already determined from what we did before is exactly the same as our tx. We only have the two forces. They must exactly cancel out. And because of the symmetry, because my center of gravity was exactly in the middle, it turns out that hy is also equal to ty. So these two, this hinge force that we've spent all this time figuring out, has identical magnitude components to our tension, which means the magnitude of our hinge force vector is going to be exactly the same as the tension. or 2261 newtons. And that also means, since it has the same components, we're going to get the same angle. So this angle phi that we set up there, this angle phi must also be equal to the angle theta, and that is equal to 25 degrees. So put that down there. Again, if you had not done things algebraically and instead plugged in numbers, you still would have found out all of these things. And in the end, you might have even noticed, like, hey, my hinge force is exactly the same as my tension, and it's at exactly the same angle. And again, that comes about because of the symmetry of this problem, because we have the center of gravity exactly in the middle. If my center of gravity is not exactly in the middle, then that is not going to happen. In fact, there's sort of a very straightforward way of seeing that the hinge force has to be the same as the tension. And that is, we think about adding all these force vectors together, what we would have done down here. Graphically, when I add vectors together, I'm using this head to tail method. But when I add them, in order to add up to 0, this must mean they always form a closed polygon. In this case, it's going to be a triangle, which means my weight force, which points like this, and my tension, which points like that, must exactly be balanced by my hinge force, which always looks like this. So in fact, it forms an isosceles triangle. And because of where this is located, those are exactly the same length. So, so this is the problem. Right, let me zoom up and see if I can capture all of it, well, almost all of it on camera here. Again, it's a little cluttered. There we go. I think we got all of it now. Again, we had our original picture. And when you're working through problems, you should always be drawing a picture. I know in the end, we're going to do a bunch of math, but if you're given a picture, copy it down. If you're not given a picture, sketch it out. Pictures are always going to help you, because then I use that to help me find out my lever arm, calculate my torques, and so on. So no one showed up for office hours, so that's fine. It's just me in the recording. There's no legal repercussions. And all right, I'm going to shut this down now and upload it. Bye.